Good morning, everybody. Happy Monday. Hope everybody's doing well today. All right. Any questions before we get started? Any questions about the exam? And so I'll just start off with a little bit of announcements. I'm just working through the grading. I think I've graded everyone's lab 3, if I remember correctly. And now I'm trying to work through the exams. I've been staying on top of those. They look pretty good from what I've seen so far. So just continue with that, and they're due tonight. And so, again, I'm pretty pleased with how everybody is doing. And just let me know if there are any grading mishaps or anything. While I was grading the free response questions, I try to go back in the exam if I notice anything amiss, especially, little typos with spelling. I tried to address those. But if you notice any and think you deserve some credit back, just email me. Any other questions before we get started? All right, so now let's go through our next chapter here. So we're starting to talk about physical changes, chemical changes, and writing reactions. So that's kind of, I think, the fun part of chemistry. And so as a working chemist, you would, write these chemical equations, but let's talk about what are our physical changes, what are our chemical changes. So our physical changes are changes that alter the state or appearance, but not the composition. So, right, we're not rearranging our atoms. And so some examples of this are water boiling, and other things would be like dissolving. Right. So if you dissolve like sugar or salt into a liquid, then it's just becoming a mixture, but you haven't actually altered it. So you haven't chemically altered it. And so chemical changes are when you alter the composition of the matter. And so most of us have seen this. So iron, for example, starts off as individual iron atoms. And then, of course, it reacts with the oxygen in the air over time and makes this iron 3 oxide or rust. And of course, we can write out our chemical formula for iron 3 oxide. We kind of just did that on our exam. And so, like I was saying, if you're a working chemist, this would be something that would be important. You would probably do this every day, write your reactions. What reaction are we running? And so, this involves writing out our equation. And so, this just gives us an overall view of what we're doing. And so, we have the reactants on the left side, products on the right side, and then we have this arrow. And so, notice it is a single headed arrow going in one direction. So this is showing that complete conversion. And so there's a lot of information packed in this statement. So it's going to tell us the relative quantities, and the quantities are going to be in what we'll call this mole-mole ratio. And this would be similar to your recipe, like making a cake. You have your ratio of cup ingredients. And then it also tells us, obviously, the substances by their chemical equation and then their physical state. So liquid, gas, gas, gas. And so we have, right, our S for solid, L for liquid, G for gas. And then you might also see this AQ, and that stands for aqueous. Oops. I don't know why. Aqueous. And so that would be something like dissolved in water. Like could be HCl or iron chloride, copper chloride. something like that. So our chemical equations, there are shorthand for describing our chemical reaction. So we get our formula. And so this is where things start to build in chemistry. And so kind of the first part is writing your proper formula, just like we just learned and practiced. So that's important. And then we want to have our states of our reactants and products. And then again, our relative number of reactants and products. And so that was, again, molar amounts. So that will be very useful. So this is really key because this relative amount is key so that other people can also replicate your experiment and know how many equivalents you use. And then from there, we can determine the amount. So once you know the formula, you can get the molecular weight of it. And then, of course, we can multiply moles by molecular weights. That tells us the amounts we'll actually be getting. And so we'll learn how to balance these chemical equations because that's really important, a good skill to have. And so we are balancing both by the law of conservation of mass, and we'll see how that works out. But we'll start by also balancing those quantities of atoms. And so just what we're about to study right now, so this kind of numerical relationship and studying our chemical quantities and our reaction and converting that to moles and grams, all that is known as stoichiometry. So super important. If you are a chemist, you will be doing a lot of this. Let's look in detail at this reaction. And so we have our CH4, so methane, plus two equivalents of oxygen, O2. This gives us CO2 and water. And notice, right, we have these same amounts in atoms as we have initially. And so let's look at our reactants. So we have one carbon, and then our products, we still just have one carbon atom. Our reactants, we had 4 hydrogens. Then our products, now we have 4 hydrogens on our water. Same thing, oxygen. So 2 times 2 is 4, and we can count them 1, 2, 3, 4 atoms of oxygen. And then our water, or our oxygen. So 2 go into CO2, 1 goes into each water. So 1, 2, 3, 4. And mathematically, we can calculate that. So 2 plus 2 times 1 here. So 2 plus 2 is 4. And so what does this stoichiometry tell us, right? It tells us the relatives amount in moles of each substance involved in our reaction. And so we can say this for individual molecules. So 2 molecules of octane react with 25 molecules of O2 to give us 16 molecules of CO2 and 18 water molecules. We can also do a mole-mole ratio. So this means 2 moles of octane and 25 moles of oxygen gives us 16 moles of CO2 and 18 moles of water. And then we can scale that up and down as well by whatever quantity we need. So now looking at our mole-mole ratio, we can go, times 1/10 or divide by 10. So 0.2 moles to 2.5 moles to 1.6 moles to 1.8 moles, right? We can scale times 200 or 100 or 200, doesn't matter. Let's do 200. Let's be crazy. That gives us a 400 mole ratio to that'd be 50, so 5,000 moles of O2 plus 3,200 moles of CO2 to 36 100 moles of water. So again, right, doesn't matter. Just whatever ratio. Let's do 100. A little easier. So 200, 2,500 to 1,600 moles of CO2, 1,800, right? We could go crazy. It doesn't matter. Whatever factor. So times 1, times 3, times 4. And our mole-mole ratio will always be the same. Questions? And so now let's go through this. And I always tell people if you can do this stoichiometry, so if you can bake a cake and figure out those ratios, right? Scale up your cake recipe half or twice or 3 times, then you can totally do stoichiometry. And so let's look at this with pizza, and then we'll look at it with s'mores and kind of work through that. And so if we're trying to make a pizza, our number of pizzas depends on the ingredients. And so for our standard pizza, we can say we need 1 crust. We could call this our mole, right? So this is essentially our 1 mole of crust. We need 5 ounces of tomato sauce. And we could say, right, 1 ounce of tomato sauce is like a mole. Again, this is just to relate it. So this is basically 5 moles of tomato sauce. 2, and again, for cheese, we'll say 1 cup is 1 mole of cheese. That's our molar cheese amount. So this would be 2 moles of cheese. And that would give us 1 pizza, right? Which is 1 mole of pizza. So they're in this ratio. And so now we can also do some math. So we can say, well, how much pizza can we make if we have 10 cups of cheese? So we have 10 cups. We said, well, each pizza needs 2 cups. And now here's our conversion factor. And so this is our conversion factor, aka our mole-mole ratio. And this is always from your balanced equation. And so this is where students often get lost. So I see them, not understanding where this conversion factor came from. This always comes from your balanced equation. So going back to this, right? So this is your balanced equation. And so now we can do our math. So 10 divided by 2, and that gives us 5 pizzas. So you can also think about this as a proportion if that works better. So we can see right there's 2 cups of cheese. I don't know why I misspelled cheese. And 1 pizza. I was thinking about that Z in pizza. Then if we have 10 cups of cheese, how many pizzas? And again, cross multiply. So 10 times 1 divided by 2 gives us 5 again. So whichever makes more sense for you, either this dimensional analysis or setting up a proportion. And so now let's make s'mores. So if you need to pull out your mental s'mores, you can pause the video, get out some s'mores. And so as you get out your s'mores, we'll have to kind of define what our mole amounts are and how you make a s'more. And if anyone's in the chat, you can, of course, chime in how you like to make your s'mores. But when I make my s'more, and let me try to get at least a mildly appropriate s'more color. Trying to pick a brown. I don't know why. There we go. Our brown. So we have 2 graham crackers here. Right. So we always start with 2 graham crackers. My nice graham cracker. You can tell I have zero artistic skill. And so I'm kind of looking at this picture for inspiration. And again, we can have a debate later on how to make the perfect s'more, but I'm going to use one jumbo marshmallow. And then let's use 3 pieces of chocolate. And so for that, I'm thinking of those little individual Hershey bars. Although now everybody likes those Mr. Beast chocolate bars. All right, so here's our balanced equation on how to make a s'more. I'll draw out my jumbo marshmallow. I already drew out my chocolate. Draw it out again. Now I'm hungry. All right. And so let's start off kind of basic. And so now let's ask, and we have about 48 students in the class. So if we want to make s'mores, for 48 students, how much will we need? How much of each ingredient? So take a minute to try this out. So pause if you need more time. Otherwise, I'll keep going unless someone in the chat screams out at me. And so again, let's refer to our balanced equation. So for every 1 s'more, and we'll start with graham crackers, we need 2 graham crackers. And so let's start off with, if I want 48 s'mores, set up my conversion factor. Well, we need to get rid of s'mores. So for every 1 s'more, I need 2 graham cracker. Let me punch this in my calculator. 48 times 2. So I would need 96 graham crackers, at least how I've defined them. And so let's keep going. So we need 1 jumbo marshmallow. So 48 s'mores. Now they're in a 1-to-1 ratio. So for every 1 s'more, we need 1 marshmallow. So then we need 48 marshmallows. And then our last one, so how many chocolate pieces do I need? So again, 48 s'mores. Then our conversion factor from our balanced equation. So for every 1 s'more, I need 3 chocolates. And so now the math, 48 times 3. So 144 chocolate pieces. That's for our class. All right, so let's try another type of problem. This is kind of giving you a taste of the problems that you'll see. Now, if I have 55 pieces of chocolate and excess marshmallow. How many graham crackers do I need? So give everybody a moment for that one. Let's start with what we know. So we have 55 pieces of chocolate or chocolates. And so now we need to figure out, well, I want graham crackers. So let's get our ratio of chocolate to graham crackers. And so we said we need 2 graham crackers for every 3 chocolate pieces. So 2 to 3 ratio. So 3 chocolates goes on bottom since I want chocolates to cancel. Now I'm trying to find graham crackers. So 2 graham crackers goes on top for every s'more here. And so now let's do our math. So do 55 times 3 divided by 2. Oh, I said that backwards. 55 times 2 divided by 3. And so we get 36 graham crackers. And we could round up or down since can't really make half graham crackers. Okay, questions about those. So this will be a type of problem that we see. And again, think about moles of reagents. And now let's try another one. So this is what we call a limiting reagent problem in chemistry. That's going to be which reagent runs out first. How many can you make? And so let's try one because everybody understands it when we talk about food, but not so much about chemistry. If I have 20 graham crackers, 18 marshmallows, and 66 pieces of chocolate, how many s'mores? All right, take a minute to look at that. All right, let's see how everybody's doing. And so this one's similar approach to what we did before. So we need to figure out now, well, how many s'mores can I make from each one of these reagents? So we start off with our 20 graham crackers. And then we need to convert this to s'mores. And we said, so every s'more needs 2 graham crackers. That means we can make 10 s'mores from our 20 graham crackers. And so now we need to repeat this with marshmallows. Now we have 18 marshmallows. And they were in a 1-to-1 ratio with our s'mores. So we said we had a jumbo marshmallow. And we only needed 1 for every s'more. All right, so that gives us 18 s'mores from those 18 marshmallows. And so our 66 pieces of chocolate. We said we needed 3 of them for every s'more. Chocolate, sorry. And so now 66 divided by 3. I'll punch it in just so we can all see. You believe me? So 22. So 22 s'mores. Now we go back. Well, which one was the smallest? Which one is my limiting reagent? aka which one runs out first? So we should see our graham crackers is our limiting reagent, aka right, runs out first. The graham cracker runs out first. Excellent. So that's how you do these mole problems. And so now let's try something different. Oh. Now let's switch it up a little bit. And I'll call this molar mass time. And so what I mean by that is, well, previously we're just kind of comparing our analogous mole-mole ratios. But generally, right, you don't just measure mole amounts of things. So that was convenient for our food. And let's rewrite our equation. So we said it took 2 graham crackers plus 1 marshmallow plus 3 chocolates and that gave us 1 s'more. And so normally, so let's pull up, let's do sodium chloride. And so when chemists are trying to figure out, well, how much of an amount we need, we have what's called our molecular weight. So we said we could add up our atoms and figure out our molecular weight or our atomic weight. And so we need to do that analogously for our little practice scenario that we're solving here. And so let's just do kind of then our molecular weights, right? So normally we would be able to add up our elements. Obviously, this doesn't work the same for our graham crackers. We could look up a serving size, and that would be analogous. So a graham cracker serving size is about 55 grams. So we'll call that 55 grams per mole for its molecular weight. And 1 marshmallow, again, going off of the jumbo size, is going to weigh 70 grams per mole. And then 1 chocolate, if we look up a Hershey bar size, is about 15 grams per mole. And so let's just start off with our warm up then, because again, we can mass balance so we don't lose any mass. So The mass initially has to be our final mass. And so how much does a s'more weigh? All right, how are we doing? So this one isn't too bad. We just have to add up everything. So let's go ahead and do that. So 55 times 2. So that's for our graham cracker. And then 1 marshmallow. So that's 70 grams. And then plus our chocolate. So 3 moles times our 15. And so that should give us a mass of 225 grams per mole for our s'more there. Let me show that. I'm going to type this out, hopefully. There we go. So if I want to make 20 s'mores, how many grams of chocolate should I buy? So now this is going to be more reflective of kind of the chemistry questions. You're trying to make something, you're holding your bottle of reagent. Well, how many grams do I need? So try this. Give everyone a little bit of time. Well, let's start this. So we have our 20 s'mores, and it's asking for grams of chocolate dough. So we need to convert our s'mores to figure out how many moles of chocolate, right? And then from there, we can convert to grams. So the first bit should feel like what we were doing initially. So if I have 20 s'mores, and now we can go to our balanced equation again with our moles. So, right, this is our mole ratio. So for every 1 s'more, I need 3 chocolates. So s'more goes on bottom to cancel, 3 chocolates on top. So now I'm at chocolates. And so now we can convert from moles of chocolates to grams. This is our gram conversion. So we can use our molecular weight of chocolate, so our 15. So now for 1 mole of chocolate, it is 15 grams per 1 mole. We can go ahead and multiply across. So 20 times 3 times 15. And so I get 900 grams of chocolate. Questions about that one? So let's try another one. So if I have 500 grams of graham crackers, 600 grams of marshmallows, and 450 grams of chocolate, what is my limiting reagent? Whoop. And how many s'mores? I'll give people a minute for this one. So if you're watching this later, go ahead and pause if you need more time. And I'm going to move forward with this, unless, again, anyone in the chat kind of flags me down. And so let's work through this. Let's kind of think about what it's asking. And so let's think about, too, analogously what it's saying. So we're saying I have 500 grams of graham crackers, right? I have 500 grams of sodium chloride. And so that doesn't tell us a molar amount, right? That's what we need to compare. So 500 grams of graham crackers, 600 grams of marshmallows, 450 grams of chocolate, but I don't have molar amounts, so I can't do my mole ratio. And so let's do that. So that's really important. So when we're doing chemistry and we see gram amounts right away, we should think, well, I can't compare them, right? So I can't compare this. They're in grams. So it's not related to our balanced equation. So we need to get it into moles so we can. Let's do that for our first step. I'm just trying to find something exciting, but I don't think you can read this rainbow color that well. So let's start with our graham crackers. And you'll see this process gets kind of repetitive, but it should also feel good. So once you get the process, you should be able to apply that to chemistry. So we're starting with our amount. So our 500 grams. And we need to convert it to moles of graham cracker. So I'll go back to my molecular weight. So it's 55 grams per mole. So I can divide this by 55 grams. That gives me 1 mole of graham crackers. So now that I'm at mole of graham crackers, I could continue on because the question is how many s'mores. And so for my graham cracker, we need to convert to s'mores. So I'll put 1 s'more on top. And we said we needed 2 graham crackers, though, for every s'more. Let's go ahead and see what that gives us. So 500 divided by 55. That gives me how many graham crackers? The moles, right? So 9.09 moles. Then we said 2 graham crackers per s'more. And so we get 4.54 s'mores. So now let's repeat that. Let's do our marshmallows. And let's see how badly I regret this color. So marshmallow. We said we had 600 grams of marshmallow. And again, same process. We need to go from grams to moles. And we said our molar mass was 70 grams per mole for our marshmallow. So, see, good thing for our units. So grams cancels, giving us with our marshmallow. And then marshmallows and s'mores are in a 1-to-1 ratio, since we use the jumbo ones. So let's see what that gives us when we punch that in. So 600 divided by 70. That's 8.57. So moles of marshmallows, and then a 1-to-1 ratio that gives us 8.57 s'mores. Questions about that one? So last one is chocolates. Now let's repeat the process for chocolates so we can come to our final answer. So our 450 grams of chocolates. Now we need to convert that to moles. So we said it was 15 grams per 1 mole of chocolate. And we needed 3 chocolates, though. And our 1 s'more. Let's see what this gives us. So 450 divided by 15. So this gives us moles of chocolate. So 30 moles. And each one needs 3, though. So we can only make 10 s'mores. And so which one was the least amount? So which one was our limiting reagent? So we had 10, 8, and 4.54. So looking at all of them, this is going to be my limiting reagent. So my graham crackers are going to run out first, and I can only make 4.5 s'mores with that. All right. Questions. So now let's kind of go to where we're going with this. We have our mole highway. And with this, I'll put, well, what is a mole? So we kind of talked about it. I'm not sure if I mentioned it prior in lecture. But let's go through it again. So what is a mole? So it's really just a quantity amount. And it's basically similar to like a dozen or a baker's dozen. So right, a dozen is 12. And so that's just a quantity amount. And the reason why it was chosen is because we wanted to make the math work out. And so something that you might have noticed is that our 1 atom of carbon is 12 atomic mass units, but also 1 mole of carbon is then 12 grams per mole. And so the reason why it works out so well is this Avogadro's number. And so we can solve for it. And this is our mole. And so how we can kind of determine this is we have 12 AMUs. And then we need a conversion factor. And so 1 AMU is equal to 1.66 times 10 to the negative 24th grams, at least roughly. Now let's convert this. So times X, so this would be Avogadro's number, is equal to 12 grams per mole. And so to solve for this, let's solve. So 12 first divided by 12, and then divided by this factor. And here we have it, 6.02. And so notice, right, we use some rounded numbers, so it doesn't work out perfectly. But Avogadro's number is 6.022 times 10 to the 23rd, and that's atoms or molecules. So that would be equal to our mole. And so again, right, we just add up our atoms from our periodic table, and that gives us our correct amount. I didn't have a periodic table up today. And so this is a good sheet that you might want to print out separately and have kind of as a reference. And so it's useful. So it tells you moles and kind of reminds you how to go from mass to moles. So either if you're going from mass to moles, divide by molecular weight. And you can derive all this from your unit canceling dimensional analysis as well. But sometimes it's good to have a backup reference, kind of sanity check. And then going from moles to grams, it tells you to multiply by your molecular weight. And then our number of moles, right, it's saying use our stoichiometry. And then if you ever see this number of particles, then you can divide by Avogadro's number or multiply moles by Avogadro's number to get number of particles. And here's also Avogadro's number there as well. I think we're doing pretty well. I'm thinking about stopping lecture here. So this was kind of like our warm up and how to put it in other terms. So that means on Wednesday, I'm going to go over kind of this mole amounts in more detail. I think we've done a lot of math. It's been a little, these chapters are math heavy. So even though it's not a lot of math, I know, it can still be exhausting. So we'll go through the stoichiometry and put together what we just did with kind of our pizza and our s'mores. We'll put it with real moles in chemistry. So make sure you feel really, really, really good about the s'mores and kind of the analogy that we've been drawing. So, right, we were saying this is our moles. We had our molar weights. And then we were able to calculate our grams and moles. And so we'll be doing just that, just except with our real elements. And right, we won't be given necessarily, at least not spelled out explicitly like we did for graham crackers, the molecular weights, right? They were given to us explicitly. But here we can calculate them, by adding them up. So we know our molecular weight for water is 18 grams per mole, for instance. But like I said, we'll pick up with this on Wednesday. This is a good stopping place. So I'll stop lecture and then I'll hang around on chat just in case there's any questions from the audience. And then, of course, you can catch me by email as well. So thank you so much. Again, I always appreciate you coming live and I appreciate the hard work everyone's doing. We're at the halfway point. So just keep pushing through. All right. I will catch you all by email. Thanks again. Have a great day.